So in this podcast, we're going to talk about the Earth's energy balance, and it is like it sounds. It's the energy that comes in from the sun, and how does the Earth reflect and absorb that energy? How does it re-radiate it? And just how does that sun's energy affect life here on Earth? And then lastly, we want to look at how do humans affect that balance. The sun is obviously a massive influence on our solar system. It's over 400,000 miles across. So you consider that, that's quite large, and that is producing an awful lot of heat. The sun in a mere hour produces 430 quintillion joules of energy. So you consider that, that's about all the energy humans use on Earth in a year, and the sun produces that in an hour. So when we consider that, that's a lot of energy, but only 1 billionth% of that energy actually reaches Earth. This is just a size comparison of the Earth to the sun. We're 93 million miles away from the sun, but yet its energy is still reaching us and affecting our Earth. The sun's energy happens through nuclear fusion. So the sun's energy happens through nuclear fusion in the core, and this is hydrogen being fused into helium. And through that process, massive amounts of energy is released. And energy is released from the sun through electromagnetic radiation. And your different forms of electromagnetic radiation vary from long wave to short wave radiation, and vary in intensity of energy. And the sun produces this from the atomic actions in the core. Long wave radiation is radio waves, microwaves, infrared waves. Visible light is a little more intense than UV light, gamma rays, and X-rays would be your more intense versions of light. Why those different wavelengths are important is because they all pass through our atmosphere in different ways. You can see by this diagram here, the windows act as an atmosphere, and what we have working through, you see the long wave radiation makes it through our atmosphere. Infrared gets a little blocked, and we'll talk about what happens there with infrared radiation when it's re-radiated from our surface in the atmosphere. And you can see visible light and radio waves pass through nice and neatly. UV light is partially passing through, and gamma rays and X-rays get blocked. And so what we have here is that shortwave radiation is typically pretty much blocked, while our longer wave radiation does make it through our atmosphere. And why that's important, the more intense waves that do make it through, they heat up our Earth's surface. So the sun's rays hit the Earth at an angle that's different all over the globe. Our Earth's axis is tilted slightly at 23.5 degrees, which changes the angle of incidence as the sun's rays hits the Earth. And this is different from season to season. The sun's going to strike the Earth differently. That's why we have seasons. But dependent upon where the sun is hitting and how it's hitting, that's going to determine the heat that's being produced in that area. Now, heat transfers in 3 different ways. Radiation happens through empty space, convection happens in fluid, so liquid or gas, and conduction happens through direct contact. And all of these different ways of heat transfer play a role in how heat is lost and absorbed in the Earth. And so when we look at this with radiation, the energy that gets from the sun is a form of radiation, and that's passing through empty space. So all the different spheres of the Earth reflect and absorb and re-radiate heat differently. And when we look at these different spheres, air in the atmosphere is going to be very different than what's going to happen on land. About 60% of the sun's energy is actually absorbed in the Earth. The rest gets reflected in various ways. And we'll talk about that in terms of what type of surface reflects or absorbs best, and what type of surface actually releases heat and absorbs heat in different ways. So let's take a look at this diagram. This is a really important diagram. This really is energy balance in a nutshell. It's also called energy budget. And so what we have here, if you look up at the top with the sun, we're going to use a random unit here of 100. So let's say 100% of radiation is coming from the sun. Well, here's what happens in terms of reflection and absorption. You can see that about 46% there is absorbed by the land. We also have some absorption in our atmosphere as well, okay, absorbed in the clouds over the atmosphere. And then a lot of it gets scattered and reflected back. And reflection has to do with the type of material and also the color of the material. So when we deal with this and we talk about where this is hitting on land or if this is hitting in the water, Water has a pretty high reflection rate, as snow would as well. This is something called albedo effect. So let's take a look at albedo effect and how this works and how this creates something called a positive feedback loop, which can really be a problem for our climate and really be a problem when we talk about man-made climate change. And so when we look at this, it's just kind of a diagram of albedo effect and how this works. So albedo effect basically is, again, the reflectivity ability of a surface. One would be a perfect value, would be a total reflection. And then the lower you got, there'd be more absorption. And so when we look at this, white surfaces tend to reflect more. So snow, ice, water is going to be more reflective than a darker surface like rock or granite or something like that, which a lot of these maybe basalt in the mountains and these areas when the snow melts away is going to have a much lower albedo effect. It's going to absorb more of this energy. So if you look at these two, this diagram kind of shows that we have the same amount of sun hitting these surfaces. You can see that same bar is reflected here, and then only partial ability there, only partial is released or let go, reflected off of that rock. And so we look at these things, this can create, like I said, a positive feedback loop. And so this same example, we get less snow, so there's less reflection, and then there's more heating. And so if you think about that, when that happens, the more snow melts, the more absorption there is of the sun's energy, the higher the temperatures go, and then the more snow melts, and then the more absorption, and then the higher the temperatures go. And it's this constant feeding into the system, this positive feedback loop. As we lose more of our surface ice, that this can lead to more global heating as well. And so that's something to consider as we put more greenhouse gases into the atmosphere, because in turn, we're going to continue to heat our atmosphere. And when that happens, more snow will melt, and again, more absorption, again, more heat, and so on. Okay, so let's take a look at this diagram a little bit closer here. So again, 100 units of energy coming in. We get absorption and reflection by the clouds. We get absorbed energy. What happens here, we talked about the different types of radiation. And so we have this re-radiation of long wave electromagnetic radiation like infrared waves. And so if you look over here, that's being re-emitted. So it's the absorption. These red numbers are the re-emission, the releasing of that heat as it absorbs into the land, into our surface, and then is re-released. And then what happens, this gets caught back in our atmosphere and again re-radiated again by greenhouse gases. So the big takeaway from this is that obviously not all energy is absorbed on the earth. Some is reflected, some is cast back. And again, that's due to a lot of clouds having a high albedo effect, just like ice. There are some ideas out there to even seed the atmosphere so we can get more clouds. And if we have more clouds, then our temperatures would drop. And so that's a way to combat man-made global warming. So that's an interesting idea. You can probably Google search and find some interesting titles there to read. So this is an infrared satellite image of our Earth. You can see not all of Earth is emitting these same wavelengths of radiation. When we're dealing with this, not all surfaces absorb and radiate heat at the same rate. Water versus land is a good example of that. So when we consider that most of our globe is water, water has what's called a high specific heat. So water holds on to its heat a lot more than the land would. So that's going to play a role in how our Earth both re-radiates heat and absorbs heat, and how our global temperatures function as well. And so when we look at this, you can see that this is also due to that albedo effect we talked, that some of this is getting reflected. This is due to the incidence of the sun. This is due to the type of land that's there. Simple way to talk about how surfaces absorb and release heat differently. If you heated a beaker of water to 100 degrees and you heated a beaker of soil to 100 degrees, and then you took them off the burner and let them cool, you would see that that beaker of water held onto its heat a lot longer. And so there's all kinds of factors that play a role in how heat is absorbed and how heat is released. The last thing I want to look at is how greenhouse gases re-release energy. And so this is a simulation that shows this really well. So this would be infrared photons, which are again those long wave, low energy waves. And greenhouse gases have the capability to capture and re-radiate those long wave photons. And so the greenhouse gas is a good thing. If we didn't have the greenhouse gas, our Earth would be a kind of a frozen planet. Um, but when we start dealing with climate change, the factor that's a little scary is that the greenhouse effect can kind of run away on us. And so let's think about how that would work. If we have this molecule here, this is CH4, that's methane. Methane's a very powerful greenhouse gas because it re-radiates a lot of heat. It does break down a little quicker in the atmosphere. And then if I choose CO2 here, you can see that it also captures and re-radiates heat. And what's happening here is not all the wavelengths are caught, but some are. And as that heat tries to escape Earth, it basically gets caught and re-radiated again. Okay, water vapor, H2O, is also a greenhouse gas and has that ability, but not all gases are. So nitrogen, which most of our atmosphere is made up of, you can see does not capture those photons, and diatomic oxygen, which we breathe and is in our atmosphere, does not capture those as well. So if we built our own atmosphere here, and then I fired off my gun, okay, you can see that again, once we have that, if you can picture all those molecules together, we get the re-radiating, and then it gets re-radiated to other molecules, which then can catch it. So that energy gets kind of caught up in our atmosphere in greater numbers. And if we would deal with that, and let's say, okay, well, CO2, we're going to keep pumping CO2 into the atmosphere, and you could kind of track those photons, you'd see that it would get more caught up in our atmosphere and get bounced around more and continue to trap more and more heat. The more greenhouse gases we put into our atmosphere, the more that heat is kind of caught up in our atmosphere. So let's think back to that diagram we looked at when the 100 units of energy comes into the Earth, and some's reflected and then some's absorbed and then some gets re-radiated back into the atmosphere. The more that number goes up for the re-radiation and the absorption in the atmosphere, the higher our global temperatures will climb. And so that's a concern that humans are causing this energy balance to get out of balance. So all of this ties together our global temperatures. And what we're going to look at next is how do humans' emissions play a factor in this role, and what can we do to limit our emissions? What are some options to limit emissions? And what's kind of our next step in terms of fighting climate change?